In this example, we're going to examine the consistency of an estimator mu hat. Now, before we talk about the estimator, we're going to think about the data that we observe, and suppose that we observe n independent identically distributed observations of xi such that the expectation of each of those observations is equal to mu x, where mu x is the population average. Now, the estimator that we're going to look at is equal to 1 over n minus 1, so that's 1 over the number of observations minus 1 times by the sum of all of those observations. Now, this looks similar to the sample mean. Remember, the sample mean, x bar, is just equal to 1 over n times by the sum of the xi's. And the only real difference is that instead of dividing through by n, we're dividing through by n minus 1. Now, formally, an estimator mu hat can be said to be consistent if, as the sample size tends towards infinity, the probability that your estimator is within a tiny amount, let's call it epsilon, of the true population parameter mu x, tends towards 1. Now, this is a slightly complicated definition, but slightly less formally, we can say that an estimator is consistent if the probability limit, or p-lim, of that estimator is equal to the population parameter being estimated. So in this case, our estimator mu hat is going to be consistent if, as the sample size tends towards infinity, it converges in probability to the true population parameter mu x. Now, we'll come back to this example in a second, but in almost any example like this, you will need to appeal to the weak law of large numbers. And the weak law of large numbers tells us that if we have n independent identically distributed observations of xi, then the probability limit of the sample mean is just going to be equal to the expectation of x. Now, in this case, because the expectation of all of those observations is equal to mu x, we could write that the probability limit of our sample mean is equal to mu x. And we're going to use that rule again and again in order to evaluate whether or not an estimator is consistent or not. So let's return to the problem. And we're going to try and find the probability limit of our estimator. So we're going to find the probability limit of mu hat which is the same as the probability limit of (1 over n minus 1) times by the sum of the xi's. Now, because we're going to use the weak law of large numbers, a good strategy to this sort of problem is to try and write your estimator somehow related to the sample mean. So is there any way that we can rewrite this expression inside the probability limit related to the sample mean, 1 over n times by the sum of the xi's? And yes, we can. We could multiply top and bottom here by n, giving our expression as this is the same as the probability limit of n over n minus 1 times by 1 over n times by the sum of the xi's. Now, we haven't changed anything here. All that we've done is we've multiplied and divided by n, which is equivalent to multiplying the estimator by 1. If you multiply out those brackets, you'll see that you still have 1 over n minus 1 times by the sum of the xi's. Now, with probability limits, if you have a probability limit of a product, you can split this up into the product of two probability limits. So you can write this as being the same as the probability limit of n over n minus 1 times by the probability limit of 1 over n times by the sum from I is equal to 1 to n of xi. Now this second expression we already know is going to be equal to the expectation of x, or mu x. So we can rewrite this as being equal to the probability limit of n over n minus 1 times by the expectation of x, or mu x. Now the last thing to do is think about, well, what is the probability limit of n over n minus 1? Well, because there's no variable in here, we can actually just think of this probability limit as the same as the limit as n tends towards infinity. As n tends towards infinity, n and n minus 1 will be indistinguishable from each other, so n over n minus 1 will converge towards 1. So we can rewrite this as being equal to 1 times by mu x, or mu x. So as that sample size tends towards infinity, our estimator converges towards the true population parameter mu x.